And we want to see whether these are unbiased or not. Is lambda 0 unbiased? So we want to evaluate the bias. Expected value of lambda 0 is expected value of minus expected value of logarithm. Let's use n to stand for 100. It's easier to write n than 100. So this indicator is a dummy variable that equals 1 if xi equals 0, and this dummy variable equals 0 if xi is not equal to 0. So that is the dummy variable defined by this event. So this expectation is the expectation minus expectation of a logarithm function of this sample average of this indicator. The logarithm function is a concave function. So if you draw the logarithm function, it is a concave function. And if you draw the minus logarithm function, then it's a convex function. That looks like this. So minus log of x looks like this. Actually, minus of log of x is going down, so it's a decreasing function. So that's minus log of x. So minus of log of x is a convex function. Convex function means that when you average up two function values, when you take an average of two function values, let's say the simple average of two function values, that average is higher than the function evaluated at the average of the two x values. So that is the function evaluated minus log the function evaluated at the average value of x, and that is the expected value of the function value. So the average of function value is greater than the function of the average value. Therefore, this is greater than minus of log expected value of this average. And this inequality has a name that's called the Jensen's inequality. So the Jensen's inequality simply says that expected value of any function is bigger than or equal to this function evaluated at e of x if this g is strictly convex. So if it's strictly convex, then this is strictly positive. So if g is just convex, not strictly convex, this could be weak inequality. Okay, so by Jensen's inequality, this expectation of the first estimator is bigger than minus of log of expected value of this sample average. But the expected value of this sample average equals expected value of this dummy variable. In the video that we talked about dummy variables, we know expected value of the dummy variable equals the probability that the event defining the dummy variable happens. So that's probability that xi equals 0. But probability that xi equals 0 is exponential to the minus lambda because xi follows the Poisson lambda distribution. So sample average of exponential minus lambda is exponential minus lambda because this doesn't vary with I. So that's minus of log exponential minus lambda, which is lambda. So what we have found is that this estimator overestimates lambda. So the estimator based on the probability that x equals 0 overestimates lambda. So in terms of unbiasedness, it doesn't have the unbiasedness property. So the second estimator for this second estimator, we can also calculate the expected value. That estimated value equals, remember again, we use n equals 100, use n instead of 100 everywhere. So that is expected value of 1 over n sum of xi. And because of the linearity of expectation, so that equals 1 over n sum of expected value of xi. And now because xi follows Poisson lambda distribution, so expected value of xi equals lambda. So that equals lambda. So that implies this equals the sample average of lambda. The sample average of the constant lambda equals the lambda itself. So that equals lambda. So this estimator is actually unbiased. Now, what about this third estimator? This third estimator is based on the variance. So we want to estimate the expected value. We want to calculate the expected value of this one. Let's see what that is. What is this? The expected value of this can be obtained in the following way. Is expected value of this variance Remember this xn bar is the sample average of xi. To calculate this, we first notice that This should be this. So we simply added lambda and subtracted lambda, where lambda is the expected value of xi. So now we expand this square term. So we group xi minus lambda together and group lambda minus xn bar together, and then write out the square. So we have the first square term plus the second square term. And plus the cross product term. So notice that this term, we work on this term now. This term equals 2 over n lambda minus xn bar. So lambda minus xn bar factors out of this summation because this part doesn't depend on I. Right, so this part doesn't vary with I, therefore it's a common term for all of these sums. So it can be factored out, and what's left is sum of xi minus lambda. And let's bring this 1 over n to the sum, so it becomes an average of xi minus lambda. But the average of xi minus lambda is the average of xi minus lambda. So it becomes the average of xi, which is xn bar, minus the average of lambda, which is lambda, because it doesn't vary with I. So that becomes minus xn bar minus lambda squared. So this is actually minus xn bar minus lambda squared. And this, notice, is xn bar minus lambda squared because this term doesn't vary with n. So average of that is the term itself. So that cancels out with one of this. So one of these terms here. So therefore, we have this.